Good morning, class. Here's Module 4, Section 5.4, Chapters 8 and 9. Chapter 9, Systems of Linear and Nonlinear Equations. Here's the pledge. Before starting the exam, please read the following. I pledge on my honor that I will neither give nor receive unauthorized assistance of various types. All right. Systems of linear and nonlinear equations. If a system of linear equation results in two parallel lines, the system is inconsistent system. The system has no solution. The graphs are parallel lines. They have the same slope, but different y-intercepts. In other words, if you solve for y, you notice m1 equals m2, but b1 is not equal to b2. But if you try to solve it, for example, by the method of addition or substitution, you get some sort of a contradiction. A false statement like 0 equals 7 indicates the system has no solution. The system is inconsistent. If the system of linear equations results in two intersecting lines, the system is consistent with independent equations. The system has a single solution at the point of intersection. The graphs are different. They have different slopes. In other words, point of intersection is the answer as long as we have different slopes. Finally, and if the system of linear equations result in a single line, the system is dependent. Consistent system with dependent equation. Dependency is the key here. The system has an infinite number of solutions. The graphs are identical. They have the same slope and same y-intercept. In other words, if you solve for y, you get exactly the same answer, in which case m1 equals to m2, b1 equals to b2. And if you try to solve it by any method, for example, substitution, addition, you name it, an identity such as 0, 0 indicates the system has an infinite number of solutions. The equations are dependent. So very straightforward. Let's start with a very simple example. We are going to solve this system by the method of elimination or addition. We notice if we multiply this one by 5, this becomes minus 5x. And the method is to get rid of one of the variables. Let's say we want to get rid of x, so we're going to multiply this one by 5, which means we are going to repeat the second one intact, and this one is minus 5x plus 10y equals negative 5. These two cancel each other, but these two, they don't. So 0 equals 1 is a false statement. Therefore, this is an inconsistent system. The solution to this system is an empty set. You can use braces or phi, a Greek letter. What about this one? If I want to get rid of the x, I'm going to multiply this one by 5, this one by 2. If I want to get rid of the y, I'm going to multiply this one by 3, this one by 7. Since they are opposite in sign, just both of them positive. For example, let's multiply this one by 3. We get 6x minus 21y equals 9. Let's multiply this one by 7. Negative 35x plus 21y equals 49. And these two cancel. These two add up to negative 29x, 58. Divided by negative 29, x becomes negative 2. You can go to one of the original equations, for example, equation 1, and plug in x equals minus 2. And you get minus 7y equals 7, which means y equals negative 1. You must check. How do you check? You've already used equation 1. You must use equation 2 to check. So minus 5 times x, negative 2, plus 3 times y, negative 1. This is 10 minus 3 equals 7. Checks. And it took me a split second to show that. And that's the idea. You must always check. So we had seen this method. It's not a big deal. And we're going to move on towards a very interesting methodology, matrices. So the question is, what are matrices? They are defined as a rectangular array or table of numbers. A matrix with m rows and n columns has a dimension of m by n. So 1, 2, 3, and going down m rows, now columns, one column, second, third, all the way n columns. And notice, for example, this is A11. In general, Aij, I represent the number which row, and j represents the column. So for example, if I say A23 means row 2, column 3, and that gives us exactly the element we're talking about. The precise location of an element is known here. So very straightforward, everybody. Now, let me erase my work. If we are looking at matrix A, and we want to mention the dimension, 1, 2, 3 rows, 1, 2, 3, 4 columns, 3 by 4. A square matrix has the same number of rows as columns. The dimension of a square matrix is n by n. So we have 1, 2, 3 rows, 1, 2, 3 columns. So it's 3 by 3. And this is an example that we have only one row, 1, 2, 3, 4, 5. So it's a 1 by 5, and we also call it a row matrix. We could have a column matrix when we have only one column and several rows. So having said that, let's discuss addition. We can add matrices with the same dimension. So obviously it's 2 by 2 is 2 by 2, okay, only. And the way we add them up, summary of matrix addition and subtraction. If A and B are both m by n matrices, then the sum of A and B, or A plus B, is a matrix obtained by adding corresponding entries of A and B. The difference of A and B, A minus B, is obtained by subtracting corresponding entries of A and B. So right here, we would add 5 and negative 4, we get 1. We would add minus 6 and 6, we would get 0. Then 8 and 8, we get 16. Finally, number 9, number negative 3, they add up to 6. That's how you add them up. If we want to add, this one is again very simple, starting with the first entry and moving on. So 3 and 0, 3, minus 6 and 4, negative 2, 6 and minus 6, 0. The bottom one, 0 and negative 2, negative 2, negative 3 and negative 4, negative 7, 9 and negative 2, 7. So it's just same location, Aij, identical location, we can add them up. So that's as far as addition is concerned. Matrix method to solve system of linear equations. So we have an n by n matrix. REF, row echelon form method. Apply row transformation to get ones along the diagonal. A leading coefficient is 1 and zeros below the augmented matrix. I'm going to show you an augmented matrix in a moment. And whatever we do to equations, for example, we can multiply both sides by the same number except 0. We can do to augmented matrix. So that's REF. Or REF, reduce row echelon form method. Apply row transformation just as that one to get ones along the diagonal, zeros both below and above the augmented matrix. Every leading one is to the right of the one above it, and any non-zero rows are always above rows with all zeros. So some examples. You see this one is 1. Okay, this one is 1. The very first entry must be 1 in a row, and above it can be any number. If we change the number above this one to 0, becomes REF, reduced row echelon form. This one is REF as well as REF, because it starts with 1, below is 0, starts with 1. There is nothing below, but above has changed to 0. Okay, this one is just REF. Okay, and our REF makes no difference because the bottom is all zeros. See, the zeros must be at the bottom. and this one 1, everything 0, 1. The bottom is 0, the top is 0. But this one, since the top are not 0, is not REF, but it is REF row echelon form, just for the sake of argument. So we use this methodology to solve the system. So we want to come up with the augmented matrix, and basically you drop the variables, okay, and you just keep the coefficients. So if we want to go with the row becomes -1, +2, -1, 5, -10y, but just make sure that all the x's, you may have more than 2 equations, are lined up, so -1 and 5 in the first column. All the y's are lined up, 2 and -10, and the constant, and you write it as such. So what do you see here? This is called the coefficient matrix, if you write just this one. This part is called, the last column is called the constant matrix or the solution matrix. And above here, this is the X column, this is the Y column. So you want to be careful. If something is missing, for example, there is no X, you have to put 0 there. And this stands for an equal sign. Okay. So now the idea is this. First and foremost, as far as the methodology is concerned, we want to make this entry 1. How do you make that entry 1? Notice, if I go back to the equation, I can multiply both sides by any number except 0, because 0 equals 0 doesn't mean anything in this case, right? So I'm going to multiply both sides by negative. So I'm going to write negative R1 is the new R1. So this becomes +1, -2, +1, and I don't touch the second row. Okay. The next step, just go down, and I want to make sure everybody understands. If you follow this methodology, first enter 1 and everything underneath. I say everything underneath, there may be more than just 1. It happened to be just 1. But if you have 10 items, first you make them 0 before you move on to the next one and make this one 1. Because this way you won't undo the process. So how do I make this one 5? If I multiply this one by 5 and subtract from this one, so I can say -5 R1 plus R2. So if I multiply this by -5, I get -5 and 5 is 0. If I multiply this one by -5, 10, and -10 is 0. This one and this one, I get +1. So what happens when we look at this one? First, let's write the meaning of it. This means, and this means 0x plus 0y equals 1, or simply 0 equals 1. This means 1x minus 2y equals 1. And as you can see, the corresponding equation for the last row, 0 equals 1, is a false statement, a row of all zeros except the last entry. So everything is 0 except the last one, if you look at it. Therefore, the system is inconsistent, and the solution to this system is an empty set. We could use calculators for matrices for the sake of argument. Here's how we use that. How to enter matrix editor. Matrix editor found by pressing second x to the power -1. Use the arrow key to the right to edit the dimension and then enter. And you can do go to the math and do REF, for example. So let me actually show you. So if I put that matrix into a calculator, I have to go with the size 2 by 3. I put this one in. Then REF, it gives me the answer at the bottom. Notice the first row may not necessarily be the way we had it because of the methodology by which they found it may be slightly different, but the last row is the same thing. Now, quickly, if I wanted to show you using a calculator, to get the matrix editor, we want to press second and x to the power of -1. And we are going to go to the right and edit. It's on A. You can go to B, C. Those are different matrices. So A matrix, we had Okay, it is already 2 by 3, but you can change it. So right here, I can change the sign. The size is 2 by 3, we keep it. And then, so you press enter, enter, and you go to the first entry. Again, we had put this matrix in, but if it wasn't there, I mean, just for the sake of argument, I can put 2 and enter. Okay, but I'm going to go back and change it. Back to -1 because that's what I want. Okay, so this is the matrix that I need. So I'm going to go with second mode to get out of that mode. Second, x to the power -1. This time I'm going to go to the math and look at various calculations it can do. Determinant. If I want to calculate the determinant, we're going to discuss that later. I'm going to move this down to REF. And I'm going to press enter. And then second X, and I'm going to bring up the A matrix, close parentheses, REF. And if I enter it, I get exactly what we had there, 1 minus 2, 1.2001. So you can use a calculator in this fashion. Again, for basics, you should be able to do it on your own. If it gets complicated, you can use a calculator for certain parts of matrices. Okay, having said that, let's solve this one. Well, let's do it by hand and then a calculator. The very first thing is to write the augmented matrix. And I'm going to go again. I want to make sure x's are all lined up, 2, -5. The y's are lined up, -7, +3, and the constant 3, 7. So that's the augmented matrix. Now, the idea is that to make this one into 1, I can multiply by both sides by 1/2, both sides of an equation. That means this row. And that's fine. The only problem is normally when you introduce fractions, addition, subtraction becomes involved. Instead, if I multiply this one by 3 and add this one to it, 3R1, okay, so I want to, by the way, I'm going to keep the bottom. The bottom is not changing. This one I want to change to 1. Okay, that's the idea. So if I there are different ways. One of them is 3R1 plus R2. So if I multiply this one by 3, okay, I get 6. With -5, I add it, I get 1. If I multiply this one by 3, -21, I add 3, I get -8. If I multiply this one, remember, multiply every piece by 3 and then add it to the second piece. So this one now times 3 is 9 plus 7 is 16. So this is the new row. So I got what I wanted. Now the next step is to make this one 0. To make this one 0, I'm going to write this one intact. And how do I make this into 0? Definitely, you can't multiply both sides by 0. That's it, because you can't multiply both sides of an equation by that. So what do? Why don't we multiply the top one by 5 and add it to this? So 5R1 plus R2. Okay. So if I multiply this by 5, I get 5 and -5, 0. If I multiply this one by 5, I get -90 plus 3 is -87. If I multiply this one by 5, I get 80 plus 7, 87. So that's what I wanted. The next step is to make sure this changes to 1. So divide everything by -87. Remember, division is a problem of a multiplication. So -1 over 87, R2 times R2. And here's the important thing. This shouldn't change. You worked so hard to get there. So the process must be very important. The methodology you use, this shouldn't be touched. So when I multiply this by any number, remains at 0. This one becomes +1. This one becomes a -1. And if we were to write it, just look at the last one, really says y equals -1. Or 0x plus 1, y equals -1. This one, 1x minus 18, y equals 16. And y is -1. You put it here and you find the x. So it's we've done that already. But what about the matrices? If I want to go with the matrices, I'm going to put a 2 by 2 matrix. This one, 2 minus 7, 3, minus 5, 3, 7. And I'm going to do REF on that. And I'm going to do RREF. If you do RREF, look at the last column. That is the answer that we've already got. So that's how you find the answer, RREF. Matrix multiplications. The product of AB of an M by N matrix A and an N by K matrix B is an M by K matrix and is found as follows. To find the ith row, jth column element of AB, multiply each element in the ith row of A by the corresponding element in the jth column of B. The sum of these products gives the element of row I, column J of AB. The product AB can be found only if the number of columns of A is the same as the number of rows of B. The final product will have as many rows as A and as many columns as B. What do we mean by that? Let's look at a couple of examples to make some sense out of this. The thing that is important, you can't just multiply any matrices. They have to match properly, meaning if you look at n by n, n by k, the number of columns, n for the first one, the number of rows, n for the second one must be identical. The resulting matrix would be n by k. So for example, let's find R times C, the product of a row vector. This is a row vector, 1 by n matrix, and column vector, n by 1 matrix. When you have one row and one column, only you can call them a vector. So having said that, it's very simple. The methodology here says, first of all, let me just write the size so everybody can see. This one is what? 1 row, 3 columns. This one is 3 rows, 1 column. And so the result would be 1 by 1. That's what we mean, 1 by 1, according to this, 1 by 1. So how do we do that? 1 times 2 plus -2 times -1 plus 4 times 3. That's the explanation here. So we start with the simplest one to make sure we understand, and we move on. So having said that, we get 2 here, 2 here, and 12. They add up to 16. You can represent it just as a number or a matrix of size 1 by 1. What about this one? First, let's look at, always start with the size because it may or may not be doable. What is the size here? 1, 2 rows, 1, 2, 3 columns. This is 2 by 3. This is 1, 2, 3 by 1. When we multiply, because these two are identical, we can do them, and the result will be a 2 by 1 matrix. So how do we multiply? We multiply the first row by the first column. In fact, for now, just for a moment, I'm going to do this. Imagine this didn't exist. Let's say this didn't exist. It would become exactly like that one, and then we're going to do it. So 2 times 12 plus 7 times 18 plus 5 times 9. And you would write that. Now we would be done. But we do have the second one. So now, the second one, let me erase my work and let me do this. Let's say now you don't have this one. How about this? 4 times 12 plus 6 times 18 plus 9 times 9. So that's what you get for the bottom one. You add them up, you get 195, 237. And as you can see, it's a 2 by 1 matrix. Very straightforward, everybody. All right, we want to multiply these two matrices, A and B, and we are going to start with the size. In fact, you check it out. So what is the size here? 1, 2 rows, 1, 2, 3 columns. B, 1, 2, 3 rows, 1, 2 columns. So we have 2 by 3 times 3 by 2. Does it work? Yes. These two must be identical. They are. So what is the resulting matrix? 2 by 2. So first, write the size. So the resulting matrix is the 2 by 2. So we are going to multiply the first row by the first column. In other words, you can even ignore this. This doesn't exist for now. And therefore, this doesn't exist. So multiply those two. -3 times -6 plus 4 times 2 plus 2 times 3. That's it. Now we are going to multiply by that one, meaning let's do this. This one doesn't exist. Multiply this to -3 times 4 plus 4 times 3 plus 2 times -2, and it goes here. And let's say this doesn't really exist. We would be done. But now we are going to multiply this. So let me erase my work. So now this one doesn't exist. This one doesn't exist. Multiply these to 5 times -6 plus 0 times 2 plus 4 times 3. Now, finally here, 5 times 4, 0 times 3, 4 times -2, add them up, and we get 32, -4, -18, and 12. As you can see, it's the 2 by 2 that we expected. Now, as far as the calculator is concerned, matrix A is 2 by 3. Let me erase my work, by the way. So matrix A, you write it. So you decide the size, 2 by 3, and you input it. Matrix B is 3 by 2. You decide on the size, and then you put it in. And now if you just go with the math, matrix A times matrix B gives you exactly what we got here. Now, what about the other way around? What about B times A? Well, remember, B is 3 by 2 and A is 2 by 3. Can we multiply? Yes, they are identical. What will be the result? The result will be a 3 by 3 matrix. So yes, we can do that. So if you put the BA in, matrix B times matrix A, you get that. And what's very important, AB is not equal to BA. Okay. The only time AB and BA are the same if the two are inverse matrices, their product is an identity matrix. Okay. And they must be square, of course, for it to work. So that's multiplication. Now, another method to solve a system of equation is called Cramer's rule. So let's look at this method of Cramer's rule, everybody. What is the Cramer's rule? Well, we're going to look at the same example we've been looking at. So we're going to discuss what is called the determinant. The determinant of a 2 by 2 matrix, if the matrix A has elements A, B, C, D, denoted by this is a determinant symbol looking like an absolute value A, B, C, D. It's the cross product AD minus BC. That's by definition. Kramer's rule for two equations containing two variables. We find X as follows. First and foremost, in general, this is AX plus BY equals S, CX plus DY equals T. So we put together the determinant of the coefficient matrix and we call it D. Okay. Then we come up with D sub X and D sub Y. For D sub X, with the X column, this is X, this is Y, this is X, this is Y. The X column is changed to SD. For D sub Y, the Y column. And the ratio of D sub X to D is X, the ratio of D sub Y to D is Y. And you can expand that to a 3-dimension and even larger. So I'm going to erase my work. X is D sub X over D, Y is D sub Y over D. D is the determinant of the coefficient matrix AD minus BC, can't be 0. Note, we replace the first column of D by the solution matrix for D sub X, notice. And we replace the second column of D by solution matrix for D sub Y. So having said that, let's start with this one. The matrix, the coefficient matrix, if you want to go column-wise, 2, minus 5, minus 7, 3. Well, let's discuss what happens in general. If D equals 0, and at least one of the determinants, D sub X, D sub Y, or D sub Z is different from 0, and then the system is inconsistent and the solution set is phi or an empty set. If D is 0, and all of the determinants of D sub X, D sub Y, and D sub Z are equal to 0, then the system is inconsistent and dependent. So there are infinitely many solutions. So if this is 0 and one of them is not, there is no solution. If this is 0 and all of it, D sub X, D sub Y, D sub Z, if we have more, are 0, then it's a dependent system. So having said that, here's the determinant that we are interested in. Determinant of a coefficient matrix, 2 times 3 minus, so let's just put the cross product, 2 times 3 minus negative 5 times negative 7. So six minus 35 is negative 29. Now, for D sub X, we're going to replace this with this. So let's put the cross product, 3 times 3 minus 7 times negative 7. 9 and 49, they add up to 58. Now, D sub Y, we're going to replace that one with the solution matrix. Now we put the cross product. And now 2 times 7 minus 3 times negative 5, 14 plus 15 is 29. And so X is D sub X over D. 58 over negative 29 is negative 2. Y is D sub Y over D. D sub Y is 29 over negative 29 is negative 1. And that's exactly what we had in the first place. So it's pretty straightforward. I hope everybody's okay with this. What about determinant of a 3 by 3 matrix? How do we do that? We decide to expand it with respect to any row. Normally, we go with the first row. If we go with this row, and we start with A sub 1, 1, and this is cross, so it becomes A sub 1, 1 times the determinant of this piece. Then they alternate the sign, minus A sub 1, 2. Let me erase this. This is always crossed out. Minus A sub 1, 2 times the determinant of what's remaining. And then plus A sub 1, 3 times the determinant of this one. So this is what we get. First A sub 1, 1 times, let's just show that one more time, times this one. Now erase it. And this goes away. So A sub 1, 2, but they're going to alternate the sign, minus A sub 1, 2 times the determinant of that one, plus A sub 1, 3 times the determinant of this one. That's how we arrive at it. Okay. Now, here's some definitions are important to know. The 2 by 2 determinants are called minors of the 3 by 3 determinant. For example, this is called M, standing for minor, M1, 1. A sub 2, 2, A sub 2, 3, so on and so on. The cofactor of a matrix is obtained from the minor of the matrix and is equal to the product of negative 1 to the power of I plus j and the minor of the matrix minus 1 to the power of I plus j, A sub 2, 2, this one. So let me explain the difference between the two. The minor is here. The cofactor is the same thing with either positive or negative number in front of it. Either positive or negative. Which one is which? This one is positive, this one is negative, this one is positive. You can alternate. Or what is negative 1 to the power of I plus j? For this one is negative 1 to the power of 1 plus 1, and negative 1 squared is 1. That's why this takes a positive edge. But if you look at this one, minus 1 to the power of I plus j means 1 plus 2, minus 1 cubed, and that's negative 1. That's why this is a positive, this has a positive sign, this has a negative sign, and so forth. So minors and cofactors are identical when this takes a positive sign, and if it takes a negative sign, they are just opposite. That's all. So I'm going to erase my work. So we decide to expand it with respect to one of the rows. Any row will do. For example, the first one. That means you should always cross out this one. So if we want to go here, we would write 5 times this. Then this goes away and this goes away, minus negative 8 times the determinant of what remains. Y minus, they alternate, or you can calculate this. If you start from somewhere, for example, here you can calculate it, but in any event, or just remember the first one is positive, everything else alternate. Positive, negative, positive, and so on. So finally, plus 6 times this. So that's how you find the determinant. So this is the cross product 5 times. This is 0, minus 8, minus 1. I want to keep the negative and negative 8. 3 times 1 is 3 minus negative 20 plus 6. I want to keep that. 3 times minus 2 is minus 6 minus that becomes 0, their product. So this is 5 times 8 minus 8 times 23, 6 times negative 6. You do the work. You get 40 plus 184 minus 36. They add up to 188, and we're done. So that's how you find the determinant if you want to go with the first row. But one thing that is interesting, you can choose any row or column. So let's elaborate on other methods. One of them is that the second method that I'm going to show you is that we put two of them side by side. Okay. We start with the very first element and we go diagonally down, second one and third one. Multiply them, add them up. Then we go with the first element on the matrix to the right. So this is one of them, this is another one. We go this way, we add them up, and the difference is the answer. So let's put this, you don't have to memorize that. Put them next to each other, two of them. Let's start with the first entry and go diagonally down, this way and this way and this way. Take a look. So 5 times 0 times 1 plus negative 8 times 4 times negative 5 plus 6 times 3 times negative 2. Now we start with the very first entry, the second matrix next to it, which is identical to that, and we go the opposite way. This way, and that way. So 5 times 4 times negative 2 plus negative 8 times 3 times 1 plus 6 times 0 times negative 5. You add those, and you add those, and you subtract the second part from the first part. You get 124 minus negative 64, which is 188. So you get the same answer. The other thing I want to mention is that you can expand this with respect to any row or column. It is easier to expand across any row with most number of zeros, like row 2, because row 2 has 0, right? Or you can go with column 2. It works absolutely the same way. Please understand, when you expand it with respect to a row or column, that row doesn't count. So cross it out. So because I want to go with that, I'm going to start, of course, with this as a coefficient, right? But remember, if this is positive, this is negative, or you can say, I want to make sure you understand why we start with negative 3, right? Why negative 3? Because we have I negative 1 to the power of I plus j. And what is this? This one is A I j A row 2 column 1. So negative 1 to the power of 2 plus 1, which means negative 1 cubed, which is negative 1. So we start with negative 3, everybody. So to start with this, minus, and then we use 3. So minus 3. And so I'm going to cross this out, okay? And I'm going to cross this out. So the matrix that I have, the determinant, is minus 8, 6, minus 2, 1. And again, as I said, minus 3. Now, the second one, let me just erase my work. The second one is 0. So 0 times anything is 0. So that's why I don't bother to write. I'm going to go with number 4. I'm going to write this is gone, this is gone. And again, remember, they will alternate. Negative, positive, negative. So minus 4 times now the determinant 5, minus 8, minus 5, minus 2. So as you can see, it's easier because one piece you don't have to calculate. So this is negative 3 times. Minus 8 minus 1 minus 6 times negative 2 minus 4 times 5 times minus 2 minus negative 5 times negative 8. This is negative 8. A positive 12 is positive 4. This is negative 10. Negative 40, it's negative 50. Negative 3 times 4, negative 12. Plus 200, 188. So this method, it makes it easier. And if it has any zeros, you use that one. That's a smart way of approaching it. Finally, if you want to use a calculator, matrix B, you put it in. That's matrix B. And Determinant of B is 188. Nice and straightforward.